Hi everyone, this is Mr. Scott, and this is your Waves Test Review Screencast. So this unit was mainly about learning how wave phenomena work and getting used to the terms that we use to describe them. So let's get started. Here we have a tuning fork, and as you can see on the tuning fork, the frequency is 512 Hertz. What that means is that as this tuning fork starts to vibrate side to side by being forced to by some type of initial hit, it should be spreading out. And as the waves spread out, they're going to start to be pushed in all directions and create a wave pattern as the sound travels out at the speed of sound. The drawing I'm doing is very basic, but it could be interpreted in two ways. This could be a transverse wave or a longitudinal wave whenever you see it with wave fronts moving out and having a specific pattern of wavelength and frequency. This, because it's a sound wave, should be a longitudinal wave. So if we wanted to find the wavelength on a drawing like this, you would just take the difference between crest to crest or trough to trough, or in this case it would be compression to compression or rarefaction to rarefaction, and now that is the length between each consecutive repeating part of the wave. Here we'll mark that with the Greek letter lambda to show that that's the wavelength. Now the frequency, if you remember, is just the amount of cycles per unit time. So for us, that ends up being an inverse second as a unit, and the frequency is measured in hertz, which is the same thing as saying seconds to the negative 1, and that's going to be the number of wave cycles that we get passing you, if you were a stationary observer, every second. It's important to note that wavelength and frequency are inverse of each other, so as the wavelength gets bigger, the frequency gets less, and vice versa. Now the amplitude, if it was shown on a drawing like this, would mean that we would have to increase the amount of darkness that we'd have, like in the Ripple Tank lab, if you wanted to show that you had more or less amplitude coming from the sound wave. And remember, the amplitude is directly related to loudness, it's directly related to volume, but it really is also intensity too, so it's just showing how much energy per second per area is being transferred out, and in this case, it would be more and more as we got darker and darker lines. And on a transverse wave, you're used to seeing it like this, where the midpoint to the trough or the crest is defined as the amplitude and not how thick of a compression we have like in a sound wave. So here we've already alluded to the longitudinal and transverse waves, which are the two major types of waves that are in this chapter. But if this transverse wave comes back and reflects off an edge, then as the new wave goes in, you might start to see something like a standing wave. And a standing wave is really just having constructive and destructive interference happening at the same time. You get nodes and antinodes, and we can mark those nodes as the places that roughly don't move. Sorry, my drawing is not as good as I'd like it to be here. But those are the parts that don't have much amplitude, or little to no amplitude, and the parts that have the majority of the amplitude would be the antinodes up at the top of the crests or the troughs as this pattern alternates on itself. Okay, so for the equations of this chapter, we had three different ways to figure out the speed of sound. One of them you've known since the second day of school, and that is that velocity is equal to displacement divided by time. We're talking about constant or average velocity. The second way that we could figure out speed of sound is to try and actually look at the medium itself. So if we're traveling as a sound wave through air, our equation to show how much faster or slower we're going to get as we go based on temperature is 331 meters per second plus 0.6 meters per second times t. And if you put in a negative value for the temperature or a positive value for the temperature, it begins to make that number of the speed of sound rise below or above 331 meters per second by 0.6 meters per second for every degree Celsius. It's important to note that this only works for a sound wave traveling through air. And there's other types of waves, so be careful when you decide which equation to plug into. The last equation you can use to calculate velocity of any wave, which is why it's called the general wave equation, is v equals lambda f, meaning that you can take the wavelength times frequency and also figure out velocity. And there's 3 out of the 5 equations we've given you in this chapter. So this chapter doesn't have a ton of math, but just making sure that you're using the right equation and applying it correctly is a big deal. One more equation that we threw at you, which really is just kind of a definition of period and frequency, is that if you know the period, you can figure out the frequency, or it's vice versa, because they're both just really inverses of each other. Which would make sense considering that frequency is measured in hertz, which is an inverse second, and period is measured in time, which is seconds. Okay, another wave phenomenon that we covered in this chapter was the Doppler effect. And this is a big deal when it comes to any different type of wave that's moving. So that's what the Doppler effect is. It's the apparent change in motion of the frequency or wavelength of a source based on the motion of the object that's making or emitting that sound. So as my tuning fork makes a sound wave and it goes outward in all directions, if my tuning fork is going to move to the right and keep changing the place in which it makes the sound wave as the first sound wave moves outward, we begin to get a pattern that would start to look something like this, where it's getting elongated on the side that it's moving away from and getting closer and closer waves on the side that it's moving towards. So the effect you'd hear as a stationary observer, as this tuning fork flew by, would be a higher frequency in the direction it's moving towards as it comes by, towards you, and then a lower frequency as it goes by, the eem sound that you might have heard in like a car going by, a siren or something on the road before. And because wavelength is inverse of frequency, it does the exact opposite. And you can see that the spacings of the wavefronts are getting smaller in front, but then longer behind, just like you'd expect. Okay, this time let's think about an object that's going faster than the speed of sound. So it's still going to do the same principle as the Doppler effect, but because it's going faster than the actual sound it's emitting, you won't hear the sound until the actual cone or shock wave of pressure hits your ear. So usually on a test, we'll be asking you to figure out how much faster than the speed of sound the object's going, and in order to do this, all you have to do is look at the radius that the sound wave has traveled out, and then compare that to the total distance that the object has traveled, knowing that they both started in the same location and in the same amount of time traveled these displacements. This means if it took the same amount of time to travel from the same place, that really the ratio of the displacements they travel is also equal to the ratio of the velocities they have. So by drawing out the radius and keeping it the same length as what the sound wave traveled in the same time, we can see that the object went about 3.5 times as far in the same amount of time, meaning that it's probably 3.5 times the velocity of sound is its actual velocity. And relating back to the Doppler effect, if we fill in the shock wave cone, you can see the constructive interference lines starting to form right on the edge of the cone, and that's the pressure wave that would hit you of air if you were ever around something that was breaking the speed of sound, creating that sonic boom. Alright, so resonance, interference, and beats were other wave phenomena that we covered in the chapter. Resonance literally means to sound again, and in order to cause resonance, you have to match the natural frequency of an object with a frequency nearby, and if you do, that frequency can set the other one into vibration. So the demo we did in class was we would ring one tuning fork, and then its waves would naturally travel to the other tuning fork, and as they did, they would eventually force that other tuning fork to also vibrate at the exact same frequency, because both these tuning forks are 512 hertz in this case. I believe it was 440 hertz in class. Keep in mind that this is different than force vibration, where when two things are connected, they can force the other one to vibrate at the same frequency. That was like the Vibit demo, or even the big boxes that we had connected to the tuning forks. Because they were connected, they were able to vibrate at the same frequency as the tuning fork and help amplify the sound. Now, if one of these tuning forks is no longer 512 hertz, but maybe it's 510, maybe it's 513, 515, whatever it might be, you start to see a difference and no longer have resonance, but you create a beat instead. So because these two frequencies are just slightly different than each other, there will be places where the crests and the troughs, or the compressions and the rarefactions, line up perfectly and create constructive interference, and then you'll have other places where they line up completely out of phase and create destructive interference. The resultant waveform would end up looking something like this, and there would be places where we'd have the destructive interference and little to no amplitude between the two waves, and then we'd have other places where there'd be a maximum amplitude between the waves because of constructive interference of the two waves overlapping. Now, as you can see up here in the top, I've drawn concentric circles that have overlapped with another set of concentric circles. And while we're at it, that's called a moire pattern that would have constructive and destructive interference in between it, and also probably create nodal lines along the way. Okay, so it's important to note that a beat and a standing wave will create patterns that look very similar, but they're actually produced in two different ways. So a standing wave is when we send in a wave of some frequency and some wavelength, and then we keep sending it in repeatedly and have the first wave reflect back on the second wave, and then so on. A beat is produced by producing two different types of wavelengths and frequencies that are very similar to each other, but not quite identical, and then we still have the interference pattern happening, but we would define it a little bit differently. So also remember that a beat you can calculate just by taking the difference in frequency, or a standing wave we start to look at the wavelengths, the number of harmonics, and as those harmonics go up, you keep going up by another half a wavelength. So one of the last things we talked about in this chapter was a simple pendulum. And a simple pendulum is actually a simple harmonic oscillator also, and it kind of relates back to our old chapter about conserving energy. If a simple pendulum is swaying, as it goes back and forth, it actually kind of turns out to be a transverse wave if it's moving back and forth while also moving up. It produces the same sine wave graph that you'd expect from a regular slinky or something else that has a vibration going through it. The pendulum also has a frequency and a period based off of where it starts and then when it comes back from the other side to the finish. So the pendulum, the total time it takes to go to and fro and go all the way down and all the way back, is the period of its vibration. And then the frequency would be the number of times that swinging is going on every single second. Here we can consider the amplitude, the amount that it's going to sway from its starting point, just like we did from the midpoint to the crest or the trough, and then we can assume that the only two things that are going to affect the pendulum and how much frequency or period it has are its length as well as the gravity that it's feeling on whatever location in the universe it is. One big misconception is that most people think the mass matters in how much frequency the pendulum has, but that's actually not true. Okay, that's it from me on your Waves Test Review Screencast, and hopefully you'll be celebrating in a couple days. See ya.